chain rule of differentiation, which is something that we have all used on several occasions before. Right, and formally the chain rule is stated as follows. If f is differentiable at a, and g is differentiable at f of a, then the composite function g of f of x, which is also sometimes written as this, is differentiable at a and the derivative itself is given as follows. The composite function's derivative at a is the product of the derivative of g at f of a times the derivative of f at a. Right? So we have all used this before. This is the familiar chain rule of differentiation. Right? So what we are going to do here is to basically give a formal argument for why this statement holds from first principles. Okay, so let's go through the proof. Now, it turns out that the proof actually requires two cases. There is first a trivial case that one needs to address before one looks at the slightly less trivial case. In this case, the trivial case is well, it's trivial just that the argument is trivial. And the case that we are going to consider first is that f of x is not equal to f of a in a neighborhood of a. Right? More formally, what I mean by this assumption is that there exists an open interval, let's say I, such that a is contained in I and f of x is not equal to f of a for all x belonging to this interval I minus, of course, the point a. Right? So this is the formal way of stating what I have written above somewhat more informally, that f of x is not equal to f of a in a neighborhood of a. Right? So except for a, there is some neighborhood around a where the function value actually deviates from f of a. The reason why you can do what this assumption allows you to do is that it allows you to multiply and divide by f of x minus f of a when I'm studying the derivative of the composite function. Okay. So in particular, under this case, we were to characterize the derivative of the composite function, we would have to look at g of f of x minus g of f of a upon, of course, x minus a. Now what I could do is write this as g of f of x minus g of f of a upon f of x minus f of a times, well, f of x minus f of a upon x minus a. Right? This representation is exactly true at all points where f of x is not equal to f of a, because so long as that's the case, I can do this multiplication and division by f of x minus f of a. Now this condition, by the assumption that we have made for case 1, is actually true for all x in the interval I except for a. Right? And so therefore this representation is perfectly good for us to study the limit of this object as x tends to a. Right? And that is exactly what we will do, because now since as x tends to a, we know that f of x tends to f of a, and so therefore the first factor here must, as x approaches a, tend to the derivative of g at f of a. Right? Why is that? Maybe a sequential definition would give you this most easily. Suppose you have a sequence xn which, without ever taking the value a, converges to a, then by the continuity of f at a, we know that f of xn must converge to f of a, and then therefore along that sequence you can see again by the differentiability of g that this first factor here would actually indeed tend to g prime f of a, right? And the second factor, again simply by the differentiability of f, gives you f prime a, right? So patching these together, we see that we get the answer. Limit x tends to a of the composite function evaluated at x minus the composite function evaluated at a upon x minus a is in fact g prime f a times f prime a, right? Which is what we wanted to show. So case 1 is the easy case where the function value in fact does not match of f does not match that at a in some neighborhood around a. Okay. Case 2 has to be handled a bit more carefully, right? Because if case 1 does not hold, that means that f of x does become equal to f of a as for x arbitrarily close to a. And so in that case, this division and multiplication by f of x minus f of a is no longer legal. Okay, so case 2 is, again, here I'm only going to write the informal version. The formal version can be obtained by negating the formal version above, right? That f of x is equal to f of a for x arbitrarily close to a. Okay. So the first thing to note is that if f of x is equal to f of a for x arbitrarily close to a, then in fact the derivative of f at a must be 0. Okay, so how do you argue this? Pick a sequence Zn such that Zn converges to a, and of course Zn is not equal to a, and f of Zn is equal to f of a for all n, right? Such a sequence can be constructed under the case under consideration, right? Since f of x is equal to f of a for x arbitrarily close to a, I can choose construct the sequence Zn such that Zn is never equal to a, the sequence converges to a, but along this sequence the function value actually agrees with f of a. Okay, so from here it follows easily that the derivative must be 0, because if you now look at the sequence f of Zn minus f of a upon Zn minus a, this sequence is identically 0. But since f is differentiable at a, the limit of this as n goes to infinity must in fact match the derivative at a, right? And obviously this limit is going to be 0 because the numerator is identically 0 for all n, right? So from here it follows that f prime a is equal to 0. So therefore, going back to the statement of the chain rule, it suffices to show that the composite function also has a derivative of 0 at a. Okay, so the argument for that will show up on the next page. Alright, so how do we show that the composite function in this case must have a derivative at 0 at f of a, at a, sorry. So since g is differentiable at f of a, there exists a constant c, there exists two things, an interval j containing, so by interval you can pretend this is an open interval j containing f of a such that the following condition is true: g of y minus g of f of a upon y minus f of a in absolute value is less than equal to C for all y in J minus, of course, f of a, right? Because at f of a this object is not well defined, right? Why is this? Because if I look at the object inside the mod, as y tends to f of a, this must tend to the derivative of g at f of a. This follows from the differentiability of g at f of a. So the fact that you have that limit as y tends to f of a implies that there must exist an open neighborhood uh, around this point f of a such that the absolute value is upper bounded by some positive constant c. Right? This follows easily just from the fact that g is differentiable at f of a. Now we will use this fact to argue about the derivative of the composite function at a. Now this is for g, right? So there is some neighborhood open interval j containing f of a such that this condition 1 holds. Now because f is continuous at a, it follows that I can also find yet another interval. Moreover, there exists an interval, again open interval, let's say I containing a such that, well, f of x belongs to j for all x in I. Right? This is a trivial consequence of the continuity of f. Since the interval j contains f of a, so I should be able to find some open interval I around a such that the function value in that open interval must also be contained in j. Now with all of this, now what we can do is pick any sequence xn within this interval I. Right, which of course doesn't take the value of a such that xn actually converges to a. So along this sequence I want to argue that the sequence associated with the derivative of the composite function has a limit of 0. So for that what we are going to do is look at g of f of xn minus g of f of a upon xn minus a. Okay, I want to argue that this fellow has a limit of 0 as n tends to infinity. Okay, how do we do this? Well, first we are going to bound this as follows. This is, I claim, is less than equal to c times f of xn minus f of a upon xn minus a. Okay, this is in fact the main crux of the argument. Now, why is this inequality true? So this inequality is trivially true if f of xn is equal to f of a, right? Because, well, both the left hand side and the right hand side are just 0. On the other hand, if f of xn is not equal to f of a, then f of xn still belongs to j. And so therefore this inequality follows from condition 1 above. If not, f of xn in fact does belong to j minus f of a, so inequality follows from 1. Okay, so patching that together, we conclude that this inequality must hold. Okay, once I have this inequality holding, it follows that the upper bound, the right hand side, tends to 0 as n tends to infinity. Right, so therefore the left hand side, which is non-negative, must also tend to 0. Thus, if you look at g of f of xn minus g of f of a upon xn minus a, this must have a limit of 0 as n tends to infinity. Why? Because this has been upper bounded by this is a non-negative object, upper bounded by something else which tends to 0 as n tends to infinity. Right? And once the limit is 0, I can kick the mod out, right? So which means that limit n tends to infinity, g of f of xn minus g of f of a upon xn minus a is equal to 0, which is exactly what shows, since this is true for any sequence xn, so it suffices to work with sequences that are contained within the open interval I, right? Because I contains a. So for any such sequence, we have shown that this new sequence g of f of xn minus g of f of a upon xn minus a must converge to 0, which in turn implies that the composite function has a derivative of 0 at a. Okay, so that completes the proof of the chain rule.